Okay, moving along here. Today we got another shorter lesson, not overly difficult. Kind of wish this was during play week, but it's okay.
Yeah.
It'll be all right.
Okay.
Now it says based on Wednesday. Is this a one-time thing? This is really good.
Yeah. Because I was like, oh, we only have like 4 lessons on that today. He's a diligent student. You have his back, man. Come on.
He's not a senior. He can't see senioritis ability.
I've known people that get senioritis as freshmen.
All the freshmen.
I had a sophomore.
AJ?
The whole freshman.
I know it's freshman year.
I had a sophomore.
All
year,
his junior
really.
year. AJ?
Okay.
It's a nice dude though.
So, I know most of the stuff that we've done so far hasn't been really math intensive, it's been heavily conceptual. We talked about the second law. We talked about the second law of thermodynamics, which states that a reaction is spontaneous always when the entropy of what increases?
Universe.
The universe. That's important that it needs to be the universe, because we know that the system and the surroundings oppose each other. Okay? If the system is more stable or more ordered, then the surroundings are more disordered. Okay? What primarily determines the entropy of the surroundings? Kind of, but I would, yes, but there's something a little bit more. What did we say was the number one determining factor?
Is it temperature of the system? Maybe.
Exothermicity. Energy leaving or energy coming in. So the primary way to determine whether or not the surroundings entropy is favorable or not is exothermicity or heat flow. If energy is, if the reaction is exothermic, is the surroundings going to be increasing or decreasing in entropy? Increasing. Why?
Because it's gaining. The system that's running is gaining energy.
Okay, making it
Or
more disordered.
random.
Yep, more random. If a system is endothermic, it gets its energy from the surroundings, slowing down the surroundings, becoming less energetic and more ordered. Now, temperature does play a factor. Remember how we said the whole giving money to a millionaire versus giving money to somebody who is poor, there's a difference. Okay? So, yes, temperature plays a part, but the driving force for determining the entropy of the surroundings is whether energy is going in or out of the surroundings. Okay? So, if I were to summarize, this is how I would summarize it. The change in S of the surroundings is primarily determined by heat flow. Change in S of the system is primarily determined by positional probability.
Sounds like a really good phrase.
Primarily positional probability,
Yeah.
Teutonic situation. Does sound real fancy.
Yeah. so-
This is kind of reviewing the first couple lessons. Okay, we talked about the system is going to become more disordered if you have more positions. Things happen on their own. They naturally go to a state of more positions because it's more likely to be in that state if there are more positions. All right? We talked about your room being a mess. It's more positions to be messy than to be ordered. We talked about picking up a deck of cards in the same orderly fashion that we threw it on the ground. Not very likely, because there's a lot more positions where it will be unorganized. Okay? And then the next day we talked about the surroundings and how if energy is going out to the surroundings or being absorbed by the surroundings, or if energy is being taken from the surroundings, that's the primary way to determine the entropy of the surroundings. And these two oppose each other, usually. So then the main determining factor then is the temperature at which it happens. That's why things melt spontaneously lower than, at temperatures higher than at the melting point or freezing point. And things freeze at a temperature lower than the melting or freezing point. Okay? Temperature is a big determining factor.
Is that why when you have a solution in water, it changes because it's more particles that will move around?
Like when you dissolve something?
Yeah.
Yeah, there's a higher positional probability of it to be dissolved in solution. For example, dissolving salt is actually thermodynamically unfavorable, which means the dissolving process requires energy. Not a lot, 3 kilojoules to dissolve salt, but it dissolves really easily, right? And that's primarily because it has a high positional probability or more likely to be in a random state if it's dissolved than if it's in solid form. Yep. So, here we go. This is kind of going back to positional probability here. It says when we're dealing with gases, primarily gases, and you can kind of look at this from the state standpoint, but if you have only gases, the fewer the molecules, the fewer the positional probability. So this chemical reaction, from a system's entropy standpoint, is this favorable? Yes. Why?
There's less configurations.
And that's favorable?
I don't know.
Right? You want more positions, right? That's favorable. What was that?
More positions
Well, usually when we think of a reaction, we think of 4, right? Correct? So, like when I'm looking at this, how many molecules do I have here? And how many here? Which one is likely to be in the 4 molecule state or the 2 molecule state? Which one has more positions? The 4. Okay? So, the forward reaction here is not, from an entropy standpoint, favorable. The reverse reaction from an entropy standpoint is more favorable for the system because you have more particles. Now, we know that that's not the only thing that applies, right? Because there's a surroundings aspect to entropy as well, right? So this could be unfavorable for the system, but it could make the surroundings very favorable. So it could be spontaneous, okay? So it's not just looking at one thing, but if I'm specifically looking at the system, I can usually determine the entropy of it based on, okay, am I going from a solid to a gas to a liquid? If I have all gases, do I have more particles or less particles? Is the molecule more complex or not as complex? Is it more ordered or not as ordered? Those things you should be able to process through just by looking at a chemical reaction. If I look at this guy, all gases here, is the forward reaction going to be favorable from an entropy standpoint?
Yeah.
I see a couple head nods, yes.
Yeah.
got more positions to have 10 than to have 9. So if you're dealing with all gases, you can usually just count the particles. Okay? Now I'm going to give you an example here or a problem to see if you can apply this. And I realize the first one doesn't have all gases, but you should be able to determine this. We're talking system here, so I want to know what the sign of entropy is. Is it positive or negative? And then why?
Going to more disorder.
Okay? And why do you think it's going to more disorder?
Going from a solid to a solid to gas.
Yeah. So not only are you got more particles there, but you also got one of those particles is highly energetic. Okay? So system's becoming more disordered. What was that? That would be positive. Positive S is favorable because S is entropy, and if you're decreasing in entropy, you're decreasing in disorder. And how about the bottom one? Why is it negative?
It's all gas. It's 3 in the left, 2 in the right.
So it's more likely to be in reactant state because there's more positions there,
Yes.
making it likely to be negative. Yeah, let's just quickly look at this. We're talking solely from the system's perspective, okay? But we know that in order for a reaction to be spontaneous, the universe's entropy has to go up, right? Not just the system's. It helps that the system goes up, but there's a competing factor. Let me show you what I mean. We just said this is a positive S of the system. Well, let's look at energy here. I went from a solid to a solid and a gas. Do you think of this as an endothermic or exothermic process? Endo. Why? The products have more energy, right? So if I started with less energy and ended with more energy, what had to happen? Energy had to come in. But where did the energy come from? The surroundings. So the surroundings lost energy. So the surroundings, entropy is probably what? They're opposing each other. This is why the driving force or the braking force of this of these opposing forces is determined by what? If these oppose each other, what is the thing that breaks the tie? Temperature. Okay? If it's at or if it's above a certain temperature, it'll be favorable, or if it's below a certain temperature, that's what is the driving force determining or breaking a tie. Okay?
So why is favorable endo for the overall change
Favorable endo?
Yeah, because you said if it's favorable, then it's positive change, and there's 45 minutes of that.
No, endo is positive change in H. Endothermic deals with heat, entropy.
So then why do you have this aspect?
Okay, so we determined in the end, for it to be a spontaneous reaction, that has to be true, right? Okay? The driving force for the system I can't spell. I'm having a bad day.
You're going to ask 13. You're good. That's not going to happen. There you go.
Okay. Okay? That's primarily determined by positional probability. This is primarily determined by heat flow. What is our number one thing when we think about heat flow helping us determine something if we're talking about heat flow? What was that? No. Heat flow. What was the one thing that if we looked at something, it told us if it was X or endo?
Direction of energy.
Okay, that maybe it's a broad question, but the answer is positive or negative that,
Okay, that makes sense, yeah.
right? If I said positive change in H, you would say exo or endo? Endo. Energy came in. Okay? If I said negative change in H, it's exo. Right? So the surroundings entropy is primarily determined by the system's enthalpy. And you're probably thinking, well, why is the surroundings determined by the system's enthalpy? But if we know the system's enthalpy, don't we also know where the energy is going or coming from? Right? If I have a negative change in H of the system, that means the surroundings is what? Gaining energy, okay? Making it more disordered, giving it a positive change in S. So we're using this to determine the sign of that. Does that make sense? So when I said, when I was talking about signs here, the sign of this was determined by the energy flow from the system. We determined that this was endothermic. Why did we determine it was endothermic? Because which one has more energy, products or reactants? Products. So I had low to high, energy had to come in, endo, right? Well, endo means a positive change in H. A positive change in H of the system leads to a positive S of the surroundings. Does that make sense? Because the surroundings, okay, is losing energy. Right. Yeah. Wait. Negative. Yep. Does that make sense now? Okay. So the surroundings are losing energy because the system is gaining it. If the surroundings is losing energy, what's its order like? Or its disorder like?
The system have a negative S.
I'm talking about surroundings. For this situation?
Oh, no.
This is really difficult, isn't it?
I don't know.
Okay. I'm gonna slow down here.
It's like short-circuited into that.
It's okay.
Lost all knowledge.
So, the surroundings entropy is primarily determined by the system's enthalpy. And that's part of it, is like these words are so close together that it's getting bogged down in our brains a little bit. I even sometimes have to slow myself down and think, and even sometimes I make mistakes. Just so I should expect you guys to be able to make a few mistakes here and there. Okay? So an endothermic process means energy came from the surroundings. Can you guys all agree, or does this all make sense, that if the system gained the energy, the surroundings... See, I even make mistakes. I'm making a lot today, guys.
I'm suddenly sensitive here. Okay. So
I know why you guys are confused now. 'Cause I can't say it right today. Does that make sense? If the system gains the energy, the surroundings lost it. Okay? Now you have to make sense of this in your mind, what the sign of the S will be. If the surroundings lost energy, is that going to make the surroundings more ordered or less ordered? More ordered. Can someone explain to Emily why, if you lose energy, you're becoming more ordered?
You're less particle motion.
Yeah, less particle motion, it's slowing down, it's becoming more ordered. High energy means high disorder. Does that make sense, Emily? Yes? Is that an actual yes or not a yes? Okay? So the reason why the entropy of the surroundings is negative is because the surroundings lost energy, making it more ordered. More ordered, so less disordered. Yes?
Well, what if sometimes it's just asking for a change in S and it doesn't specify like surroundings or.
Usually it's system, unless they if they specifically tell you surroundings, if they don't tell you, it's going to be the system. Okay? They will specifically ask for surroundings if they're wondering about the surroundings. Does that make sense? All right. I'm not too worried. I know we only got 4 minutes, but the last part of this is actually just flat review from last year. Okay, this is just Newton's third law of thermodynamics. It's the absolute zero law. I'm not 100% sure why they throw this in here, but usually I break it down to be a little bit simpler than it actually is. Really what the third law says is that there is an ideal state that can never be attained. And that ideal state is a crystal getting to absolute zero. 0 Kelvin is an unattainable ideal. Okay? Well, a lot of times we use it as a standard because it's the first place of no energy. So it's pretty easy to use it as a standard. Okay, but it never is achieved. You guys remember absolute zero, right? That's when particle motion appears to what? Stop. It's not attainable.
That's a little
That we know of, at least at this point. What?
It's a little dangerous too.
Yeah, I'm not 100% sure. Right?
But I don't really know.
But do you guys remember this equation? Does that equation look familiar? Looks like the enthalpy equation, right? Products minus reactants. Same thing here. If I can take the product entropy and the reactants entropy and find the difference, I should be able to tell you whether the reaction is favorable or not favorable from a system standpoint. So what I wanted you to do here, I'm assuming you can do this without my help. In the back of your book, you have your S values.
Page 20, actually.
A20.
Yep.
Okay? You have your S values. Remember that when you're finding your change in S, it's the products minus reactants. Okay? Also, why are these important?
To multiply it by the S.
Because the numbers in here are per what? Look at the units for the S. Per 1 mole. So if I have more than 1 mole, I need to multiply by the coefficient. So you're going to take 2 times the S of that, plus 2 times the S of this, minus your reactants. Okay, why don't you do that? And I'll give you the answer. And if you don't get it, stay with me for a sec so I can find your problem. Quick, we get down the answer yet? I want to make a couple little quick connections here. Look at the values that have large entropies. This one has a high entropy, and this has a high entropy. Any idea why those two have high entropies? See? Why that one has a high entropy, and why that one has a high entropy?
Yes.
Yes. Okay? They have more energy, so they're more disordered. That's why they have high positive entropy values. Okay? Just help to make a little connection there. That typically the numbers that are higher. This is why, if these were both gases and these were both solids, you could almost always predict what sign it would be. Right? But since I have one solid and one gas, I'm not going to be able to predict exactly without doing the math. Now, one last thing. I know I am running a little late, but this, okay, is that favorable from a system standpoint?
Yes.
It's negative. What does negative mean?
Exothermic.
This is exothermic is for H. H values. You're getting the signs of H and the signs of S mixed up. Positive S means an increase in disorder. That's favorable.
Hey, so I was right for
So
once.
you want that?
You want disorder, yes.
No, let it go.
Guys, I was right for once.
Let's give it.
I was like positive. Hey, Grant, what size do you wear?
I don't know, that's why is it so low? This is the
Why?
That's not a
My size.
I think
Why are you?
You're too general. It's just like slightly.